Thermodynamic systems. In this unit, we will be discussing thermodynamics. Thermodynamics is the study of the relations between heat, work, temperature, and energy. Thermodynamic systems have properties that are determined by the interactions and properties of their constituent parts. A block of copper might be the system we're interested in, an object that is comprised of many atoms that are interacting with each other. We will also focus heavily on gases and how the molecules that make up a gas determine the macroscopic quantities of the gas, like pressure and temperature. In the fluids unit, we learned about pressure. For a gas, the constituent particles are flying around, hitting the sides of the container. All of these tiny collisions are forces pushing outwards on the walls. Depending on the surface area of the walls, we can derive the pressure due to the gas. Remember, pressure equals force divided by area. We will make some assumptions about gases. They will have constant mass, so no molecules are going to be escaping. They have a variable volume, which means they're compressible. We can change the size of the container. Gases also have a variable density, and they fill their entire container. Physical properties of gases include pressure, volume, and temperature. The relationships between these quantities were studied by a progression of scientists, including Boyle, Charles, and Gay-Lussac. Open the PhET gas properties simulation by clicking this little globe here. Add gas to the container by using the pump. Then click Hold Constant Temperature. See what happens to the pressure when you make the container larger and smaller by dragging the handle on the left side. Alright, so here we're going to click Ideal, and we'll go over what ideal gases are very soon. We're going to add some gas, like that. Now we're going to hold the temperature constant. Let's add some more gas. So we can see the pressure is increasing as we add more gas, because there's more collisions taking place, right? More molecules are hitting the sides of the container, increasing the pressure. Now, what do you think is going to happen when I make this container smaller? Well, there's going to be less distance for these to travel before they hit the walls. Therefore, the pressure should increase. Let's see. And you can see it's increased a lot. There's a lot more collisions taking place. Now, as I make the container large, now these molecules have to travel much further before they even reach a wall. Therefore, there's less collisions taking place against the edges of the container, and therefore there's less pressure. So, as you make the container larger, but you keep the temperature and the amount of gas constant, the pressure decreases. Pressure and volume are inversely proportional. If you compress a gas, which means you make the container smaller, while keeping the temperature and the amount of gas constant, the pressure will increase. A PV diagram has pressure on the y-axis and volume on the x-axis, and we will be talking a lot about PV diagrams in this unit. Different temperatures are going to give us different PV diagrams. Now these drawings here, these lines, are isothermal processes. An isothermal process is when the temperature is held constant. So you can see that as the volume decreases, this line goes up because pressure is increasing. As pressure decreases, you can see that the volume is increasing. So all isothermal processes will look like 1/x graphs on a PV diagram. And you can see that two gases at different temperatures are going to have different isotherms or isothermal graphs, because the higher temperature gas will be up here, the lower temperature gas will be here, but the shape of that graph will be the same. Now change the PhET simulation to the Hold Constant Pressure T option. See what happens when you increase the volume of the container while holding the pressure constant. Okay, so, well, first I'm going to make this smaller. Alright, so here's our pressure. We're going to hold the pressure constant while we're changing the volume, and we're going to see what happens to the temperature of the gas. Alright, so we're going to increase the size of the container, but if we want to maintain the same pressure, That means there has to be the same amount of collisions taking place. So what do you think is going to happen to the temperature? Well, you have to increase the temperature. See how that little flame showed up here? By increasing the temperature, we're increasing the kinetic energy of all of these molecules on average. Therefore, they're moving faster and having more collisions. And we will go more into kinetic theory next, like later. But it's important to note that if we then make the volume smaller, but we want to keep the same pressure, that means we need less collisions. So we should see some ice show up in the bucket. You have to decrease the temperature so that there's the same amount of collisions taking place as there were when it was a very large container. So, in conclusion, as you increase the size of the container, the flame appears below the gas. In order to increase the size of the container while maintaining the same pressure, you have to also heat up the gas so that you have the same amount of collisions taking place. Volume and temperature are directly proportional. Now click Hold Constant Pressure V. See what happens to the volume when you heat up or cool down the gas while keeping the pressure constant. All right, so we're going to keep the pressure constant and we're going to change the temperature and see how that affects the volume. So if I heat it up, these are going to be moving around faster, which would increase the pressure. However, we're trying to keep pressure constant, which means this shape container can change. This might be a balloon with a gas inside that can expand, or it's a container with a piston that is movable. Let's see. So we want the same amount of collisions taking place, which means as the volume increases, the gas has to heat up in order to move faster to have the same amount of collisions taking place so that the pressure is the same. And if we cool down the gas, you can see the volume decreases so that that pressure stays the same. As you heat up the container but keep the pressure constant, the volume of the container will increase. Volume and temperature are directly proportional. When you graph volume versus temperature, you get a linear relationship. You get a line, and the pressure of the gas will help to determine what the slope of this line will be. This is an isobaric process. That's when the pressure is held constant. Now don't be confused. This is not a PV diagram. A PV diagram is always pressure versus volume. This is just volume versus temperature to show you this linear relationship. Now click Hold Constant Volume. See what happens to the pressure when you heat up or cool down the gas. All right, so we're going to hold the volume constant and we're going to heat up the gas. Now, what do you think is going to happen to the amount of collisions taking place? Well, as we heat up the gas, the particles are going to move faster. Therefore, there will be more collisions on the outside of the container, on the inside of the container, outwards. Therefore, the pressure should increase. Let's see. And there we go. As you heat up the gas, the pressure increases. All right, and if we cool down the gas, and remember the shape of this container is constant. You could think of this as a container with a locked piston that's unchangeable, right? So as we cool down the gas, they're moving slower, therefore less collisions are taking place, therefore the pressure is decreasing. In conclusion, as you heat up the container but keep the size of the container constant, the pressure will increase. Pressure and temperature are directly proportional. When you graph pressure versus temperature, you get a linear relationship, and the volume of gas you're dealing with will help to determine the slope of that line. An isovolumetric process is when the volume is held constant. Another term for constant volume is isochoric. And once again, this is not a PV diagram. This is pressure versus temperature. So whenever you're looking at graphs like this, make sure you are paying attention to what is on which axis, right? So pressure, volume would be a PV diagram. This is pressure versus temperature. All of these relationships can be combined into a single general relationship for the pressure, volume, and temperature of a fixed quantity of an ideal gas. So pressure and volume were inversely proportional, and both of those were directly proportional with temperature. But if we want to turn this proportionality sign into an equal sign, we need N and R. PV equals nRT is the ideal gas law, where lowercase n is the number of moles of gas and capital R is the universal gas constant with a value of 8.31 joules per mole Kelvin. Moles. You might remember from your chemistry class, but what is a mole of gas? Just as a dozen means 12 and a couple means 2, a mole means a specific amount of molecules. A mole is the number of atoms of carbon-12 that would have a mass of 12 grams. That number is Avogadro's number, 6.02 times 10 to the 23rd molecules. There are this many molecules in 1 mole of gas. Since gases are comprised of such a large number of molecules, sometimes it is easier to use the unit of moles instead. So imagine that there were this many dots in this picture. This whole thing would be 1 mole of gas. When you use the ideal gas law in the PV equals nRT form with moles, the constant you use is capital R, 8.31. However, there is another form of the ideal gas law that uses the number of molecules instead of the number of moles. PV equals nKT. Since capital N, the number of molecules, is much larger than lowercase n, the number of moles, you need to use a different constant. Instead of capital R, you use K sub B, the Boltzmann constant, which is 1.38 times 10 to the negative 23rd joules per Kelvin. While you could first convert the number of molecules into moles and then use PV equals nRT, it is easier to just use this alternate version of the ideal gas law. On the AP2 equation sheet, the ideal gas law is included as shown. PV equals nRT equals nKT. If you are given the number of moles of a gas, use nRT. If you're given the number of molecules of a gas, use nKT.